Assalamualaikum warahmatullahi wabarakatuh. Good morning. My name is Muhammad Kamil Wan Ibrahim from Program of Mechanical Engineering. Today I would like to present my findings on the evaluation of molybdenum disulphide as an additive in vegetable oil. I would like to present according to this arrangement. First, on the project background, problem statement, objective, background theory, project methodology, result discussion, and conclusions. So the motivation of this research is vegetable oil can be used as a lubricant, because it's environmentally friendly lubricants produced such as vegetable oil and mainly used in industrial applications, especially in food industry. Vegetable oil are renewable resources and environmentally friendly lubricant, and properties of vegetable oil are high lubricity, low volatility, high biodegradability, low toxicity that make its potential to replace the mineral oil. The lubricant formulation is being developed due to limitation on the physiochemical properties of the vegetable oil, and without the presence of additive oil, vegetable oil cannot be used as a two-way friction. This is because vegetable oil alone produces low coefficient of friction and has poor thermal and oxidation stability. Therefore, the vegetable oil requires some modification in order to produce better base oil. Okay. This is the advantage of vegetable oil as a lubricant, as mentioned before. However, it has limitation. Vegetable oil has limitation in terms of poor thermal stability and poor oxidative stability. And vegetable oil alone as a base oil is impractical. Hence, we have to put some additive, and molybdenum disulphide has been chosen as a friction modifier additive. This is because it is environmentally friendly additive and provide lower coefficient of friction, flexible layer. So our objective is to measure the coefficient of friction at different load and concentration of molybdenum disulphide in terms of weight percentage in three oil. First is coconut oil, castor oil second, and the third is anti-fruit bunch bio-oil. To determine and compare, the second one is to determine and compare the optimum percentage of value of molybdenum disulphide in coconut oil, castor oil, and EFB oil based on the trend of load. The last one is to measure the wear scar based on the weight loss of the ball bearing at the optimum percentage value of MoS2 in the coconut oil, castor oil, and anti-fruit bunch bio-oil. So the theory is, to calculate the friction coefficient, we have to use a 4-ball tribological tester that it has a 4 ball bearing, 3 at the bottom and 1 ball on the top. So when we apply the load while it rotating, it can measure the coefficient of friction based on this formula, that is mu equivalent to torque multiplied by square root of 6 divided by 3 times applied load and the radius, okay, to the ball axis, that is fixed to 3.67. So the methodology is we have to prepare the lubricant in five specimens for each oil, and then we apply in the 4-ball tester, and then we interpret the results, okay, for data analysis. So for lubricant preparation, we have 3 oil, coconut oil, castor oil, and EFB. Both have the same percentage of molybdenum sulfide, 1.5, 3.0, 4.5, and 6.0. So to calculate the weight percentage is the mass of molybdenum disulphide divided by mass of 50 ml of base oil plus mass of molybdenum disulphide times 100. This is the property of coconut oil, castor oil, and EFB oil. For kinematic viscosity at 40 Celsius, coconut oil show 24.8 millimeter square per second. For castor oil, 220.6 millimeter square per second, and bio-oil, EFB bio-oil is 1.1 to 2.2 millimeter square per second. For pH, all of the oil is acidic. For coconut oil is 5 to 5.4 pH. For castor oil 5.5, and for EFB bio-oil is 4.1 to 4.93. For density, coconut oil shows that 0.919. For castor oil 0.95, and EFB bio-oil 0.8655 to 1.043. For flash point, the coconut oil showed 325 Celsius. For castor oil 250, and EFB bio-oil is more than 48 Celsius. For pour point, the coconut oil shows 21 Celsius, castor oil negative 21, and EFB bio-oil less than negative 9 Celsius. This is preparation of the lubricant. Okay, we wait for 50 ml and then put some additive. Then we mix, and we provide 5 types of mixture: 0, 1.5, 3.0, 4.5, and 6.0. This is 4-bolt tester. Okay, and we submerge the 3 balls with the oil, and we put the ring so that the ball doesn't move, and we put on top of it is the single ball, and connect to the 3 balls and rotate while applying load at 100 Newton, 200 Newton, 300 Newton, and 400 Newton. So for data analysis, we use the standard STM D51883, and then we record the frictional torque and sliding time, shows in the computer, and calculate the coefficient of friction using equation number 1. Same as the wear analysis, we use the same test, but we measure the weight of the ball before and after the test using electronic weighing scale, and observe the wear scar produced on the surface of the ball bearing using optical microscope. So this is the result: the coefficient of friction at different load, average coefficient against load, and comparison optimum concentration of molybdenum sulfide between coconut oil, castor oil, and EFB oil, and the wear scar analysis at the optimum concentration of molybdenum disulphide. So number 1 is the coconut oil. Pure coconut oil show the highest coefficient of friction as increase in the load, and the coconut oil has a low thermal efficiency and low temperature properties, thus result in increase of COF, coefficient of friction. And addition to molybdenum sulfide show reduction of coefficient of friction. However, as increase in the load, the coefficient of friction within the addition 1.5, 3.0% of the molybdenum sulfide result increase of COF. Optimum concentration molybdenum sulfide mixed with coconut oil at 4.5 shown in the graph. At 300 Newton, the COF is 0.025296, and further increasing load to 400 is lower than that, that is 0.0242. So pure castor oil showed increase of for castor oil, pure castor oil show increase of COF as increase in load from 100 to 400 is trending. And the addition of molybdenum sulfide result improved tribological performance of the test lubricant, which reduced the coefficient of friction. The optimum concentration of molybdenum sulfide mixed with castor oil is 3.0% as shown in the graph, or 300 of the COF is 0.015, and further increasing load to 400 Newton is the COF is 0.014. For empty fruit bunch oil is the least vicious. It was noticed that there's a slightly reduced in coefficient of friction at 100 to 100 load due to reducing in sliding time, meaning the testing time is shorter because it has the two balls are welded to each other. Increasing in the load from 200 Newton to 400 Newton result increasing of COF, greater formation of wear between two contacting surfaces that because of the lubrication starvation. Optimum concentration of MoS2 mixed with EFB oil is 1.5% as the COF is high at 100 Newton, which is 0.0089 and slightly dropped to 0.0064 at 200 Newton. So EFB Bio-oil has the lowest coefficient of friction followed the castor oil due to decrease in sliding time as the load increase. However, by the end, it has the balls are welded to each other, and coconut oil show the highest COF of as the lubricant is able to sustain for 60 minutes of running time. Okay. So the wear scar analysis at the optimum concentration of molybdenum sulfide increase the applied load result increase of the wear on the surface of ball bearing. So according to the Farhana, increase the applied load lead to increase in real contact between two rubbing surfaces causing the high loss of metal. So castor oil and EFB Bio-oil show the greater increase in wear at 400 Newton. The ball bearing is welded due to reduce in the lubricant film between two contacting surfaces. So the conclusion is the addition of MoS2 as additive coconut oil, castor oil and EFB Bio-oil show the reduction of coefficient of friction to pure vegetable oil as a lubricant. This is due to the prevention of metal-to-metal contact, whereas the molybdenum sulfide is able to form boundary film of the sliding contact between the two sliding surface ball bearing. The optimum concentration of molybdenum sulfide in coconut oil, castor oil, EFB Bio-oil are present at the concentration 4.5, 3.0, 1.5 respectively. Low concentration of molybdenum disulphide in castor oil and EFB Bio-oil as the sliding time decrease. This is due to properties the castor oil which is high viscosity and EFB Bio-oil has low viscosity and high acidity of oil. At the optimum concentration molybdenum sulfide in oil, the wear produces of the surface of the ball surface before the ball bearing increase as the load increase. A coconut oil showed better sliding time as the load is increased due to the greater formation of wear on the surface of ball bearing. However, the castor oil and the EFB Bio-oil result shows that the 400 ball bearing are welded to each other, which is due to the greater formation of wear and reduce in lubricant film between two contact surfaces. I think that's all from me. Thank you very much.